Carlo. Good morning to everybody and welcome to this first online analytical training. Today we will focus on the analytical troubleshooting of Velp NDA series elemental analyzers. Just 2 words about the agenda of the today training. We will have a brief introduction about Velp NDA Duma analyzers and their application fields. And then we will see the analytical procedures. Then I will leave the word to my colleague Matteo Bassani, that is here today with me, that will be the main presenter of this today training, about the analytical troubleshooting. We will see how, when we face an issue, an analytical issue, which we will analyze which will be the causes and which will be the corrective actions that we need to take in order to obtain reliable results on our samples. We will focus also on the Duma software, and we will see how to set an analysis, how to create a calibration curve, how to perform a leakage test, and how to check the consumables. Then we will have a very short verification test at the end of this analytical training. If you have some questions, I kindly ask you to write them in the chat, and then we will follow up with an answer. Okay, let's focus to the elemental analyzers. In 2010, Velp introduced the first elemental analyzers, that is NDA 701. It is the first analyzer for nitrogen and protein determination, and it works with helium as a carrier gas. Then, a couple of years later, we introduced the NDA 702. Also in this case, it works for nitrogen protein determination, but it is dual carrier gas. What does it mean? It means that it can work with both helium and argon as carrier gases. Without any extra accessories, you just need to switch on from one carrier to the other one. Then, some years ago, we introduced the last CN802, the carbon-nitrogen analyzer for carbon and nitrogen determination. Also in this case, it works with 2 carrier gas, helium and argon. All Velp Duma analyzers works in accordance to the official methods that are the official analytical worldwide organization like AOAC, ISO and EPA. For the nitrogen determination and with the protein conversion factor, you can obtain also the percentage of protein on your samples. So, which are the application fields of Velp elemental analyzers? As we can see from this cake, the main application field is for food and feed determination, especially for cereals and feed for animals and dairy products, both for R&D and quality controls. We have also application fields in the environmental one, pharmaceutical and chemical ones. Now I will leave the word to my colleague Matteo Bassani that will introduce you the working principle of Velp NDA 701 and 702. Thank you.
Okay, thank you, Paola, for the introduction. And now we see the analytical procedure of the Duma method. So the Duma method is divided into different steps. So after the sample preparation, the sample is loaded inside the autosampler disk, and it falls inside the purge chamber. Here, the helium or argon carrier flow helps the removal of the nitrogen from air. After this step, the sample will fall inside the combustion reactor if, thanks to the high temperatures, over 1000 degrees, and the presence of an oxidative catalyst, the Velp catalyst, and the oxygen atmosphere, the sample is degraded to its oxidized compounds like nitrogen oxides, water, and carbon dioxide. After this step, the carrier gas takes the combustion products to the water trap 1. This is a physical trap that removes up to the 99% of water. After this step, the combustion products reaches the reduction reactor, where thanks to the reduced copper, the nitrogen oxides are converted into elemental nitrogen, and the oxygen in excess is removed. After this step, the sample reaches the water trap 2. This is a chemical trap filled with anhydrone, and the last 1% of water is removed. Before arriving to the TCD, the CO2 is removed by the CO2 traps. These are molecular sieves that at room temperature are able to capture the carbon dioxide and release them when heated. So only elemental nitrogen will arrive to the thermal conductivity detector. Okay, these steps takes around 3 minutes. Okay, so the thermal conductivity detector is defined low gas, so low gas consumption. This is thanks to the work of the R&D department that developed a thermal conductivity detector that works without a reference gas. So in order to reduce the consumption of the carrier gas. The TCD of the NDA 701 has a limit of detection, or LOD, that is 0.003 milligrams of nitrogen. And NDA 702, the limit of detection depends on the carrier gas that you are using. If the instrument is working with helium as carrier gas, the LOD will be 0.001 milligrams of nitrogen, while when it is working with argon, is 0.001 milligram of nitrogen. The TCD guarantees reliable results. In fact, Velp takes part to the BPA proficiency test for the feed samples. So every month, the BPA circuit sends us samples that comes from the feed sector. We analyze them with the Velp elemental analyzers, and we give them back the results. So after they have the results, they give us a feedback with the range of the results and the score. So if the results are satisfactory or not. Okay, so once the elemental nitrogen has arrived to the TCD, the DUMA software records the signal. And to perform a quantitative determination of the nitrogen inside the sample, it's necessary to create a calibration curve with a certified standard that has a known nitrogen content. This is important because thanks to the calibration curve, the DUMA software can correlate the area of the peak to the milligrams of nitrogen. Once the calibration curve is ready, the software automatically calculates the nitrogen content, the percentage of nitrogen and protein, and if analyzing multiple samples, you can calculate the standard deviation and the relative standard deviation. Okay, now we will have an overview of the DUMA software. Okay, as you can see, the DUMA software is divided into 3 areas. On the main window, you will find the database with the list of all the samples that have already been done and all the samples that want to analyze. It's very easy to fill this field to start an analysis. You just have to select the new row, enter the sample name, in this case the ADTA standard, the sample weight, so 50 milligrams, the method that you want to use to analyze your sample, EDTA, what type of analysis you are performing. So in this case, the test type is a sample, and the calibration curve. Okay. On the bottom of the main window, you can see the graph of the nitrogen peak and the results. So the nitrogen percentage, the nitrogen content expressed in milligrams of nitrogen, and the protein percentage. While on the right side of the window, you will find the status of the instrument. So all the parameters that you have to check when the instrument is working. In this case, all the parameters are green, so the status is okay. Okay, so now let's move on with the presentation. Okay, now we are going to talk about the analytical troubleshooting. I will leave the word to my colleague, Paola.
Okay, just a few words about what we will see today about the analytical troubleshooting. Okay, so today we will focus on different 5 analytical troubleshooting that you can face during your analysis. We will analyze why you can face these issues, and we will analyze which will be the causes of these analytical troubleshooting, and which will be the corrective actions that we need to take to solve this issue. Starting from the first one, that is high blend value. Then we will see when we can obtain peak even if we analyze in a sample, or if we obtain a strange shape of the peak. And then when we analyze the first samples, when we get or low precision of the results or low accuracy. So let's see when we obtain a correct shape of peak, and then we will see the first analytical troubleshooting.
Okay, so before starting with the analytical troubleshooting, what is a standard peak? So how it should appear? A standard nitrogen peak has a symmetric shape. It's a single peak and has a regular area that is easy to be quantified. After that, let's start with the trouble number 1, high blank value. So when you analyze an empty tinfoil, the results of the blank should be an area lower than 100 milliwatt per second. And the detector line should be flat. In this case, you can see that the graph shows a peak. So we have to investigate the causes of this peak in the empty tinfoil. The first possible causes, it could be that the tinfoil is contaminated. So how a tinfoil can be contaminated? So when you enter a tinfoil, if you enter it without gloves, some dirtiness or grease on your hands could remain on the tinfoil. So we recommend to handle them wearing protective gloves. This is very important because Velp original tinfoils are nitrogen-free, so no peak should have been seen when analyzing them. Okay. Here is an example. So just take the tinfoil from the box and make a small sphere wearing gloves. So then you can put it inside the autosampler. Okay, the second cause could be that the protection disc on the autosampler is missing. So why is this so important? Because as I told you before the samples falls inside the combustion reactor, it is sparged with helium or argon in order to remove all the nitrogen from the air. So if the protective disk on the autosampler is missing, this step will fail. So in order to solve this, just check before starting the analysis that the protective disk is on the top of the autosampler disk. The third case is that the autosampler is dirty. The autosampler can get dirty when the tinfoil from the previous analysis wasn't closed properly. So some sample could escape from the tinfoil and remain inside the autosampler. So when you perform an analysis of the blank, the dirtiness will arrive into the combustion reactor together with the tinfoil, and you will get a nitrogen peak inside at the end of the analysis. Another cause could be that the purge system itself doesn't work, so you don't have the purge of the tinfoil, and the air is not, the atmospheric air is not removed separated from the sample. These last two steps can be easily avoided performing the preventive periodic maintenance. So if you perform this maintenance periodically, you ensure to avoid this issue. The last, again, another cause could be that the gas purity is not correct. We recommend to use a carrier gas and the oxygen gas that have a purity grade of 5.0. And so you can check this on the DumaSoft thanks to the you can check this on the DumaSoft thanks to the function oxygen is changed to carrier. You just need to go into the system menu, analysis condition. Under the voice, oxygen is changed to carrier. Move the flag from off to on. Thanks to this function, you can check both the purity of helium or argon and of the oxygen. Okay, the last cause could be that there is a leak inside the system. So this leak could be a way in from the atmospheric air, so nitrogen could reach the TCD. So we suggest to perform a leak test inside the service menu, leak test. Okay, so we suggest to go into the service menu, leak test, and perform a leak test complete. This takes just a couple of minutes. At the end of the leak test, you will get a result, test okay or test not okay. Thanks to the DumaSoft, if the leak test result is not okay, you can check, you can perform a single leak test for every specific area of the DumaSoft. So in order to identify the leak and fix it. Okay, so now we just wait a couple of minutes to see the result of the leak test. Okay, so the last week on Tuesday, there was a service training that was focused on the leak test, so we will not go further into this topic. Okay, so the leak test result is okay, so we are good to proceed. Okay, the second trouble is when you are performing an actual analysis, so the analysis of an actual sample, but no peak will be found at the TCD. So again, we have to investigate the causes of this issue. The first cause could be that once you prepare the sample, you didn't load them inside the autosampler disk. So before starting the analysis, just check that the samples have been loaded inside the autosampler disk. The second cause could be that there is no correspondence between the database list of samples and the samples inside the autosampler disk. And why this is so important? Because there is no correlation between the number on the autosampler disk and the series on your database. So when you start a series of analysis, you have to remind that the first position to be filled is the one indicated by this metal rod. So the first position to be filled is this one. This is very important because if you don't start from this position, no sample will be loaded inside the combustion reactor, or worse, the wrong sample will fall inside the combustion reactor. The third cause is that the autosampler is not moving. The autosampler is a pneumatic system that needs air to move. So if it doesn't move, the sample cannot fall inside the combustion reactor. So before starting the analysis, check that the pressure is free bar. That is the pressure recommended to guarantee the rotation of the autosampler disk. Again, we recommend to check the presence of possible leaks because if any leak is present, the carrier, the flow with the combustion products cannot reach the TCD. So no peak will be recorded. The trouble number 3 is when the peak has a strange shape. So it's not symmetric like a standard nitrogen peak should be, and it has a tailing shape. In this case, the results are higher than the expected because the area is too high. Again, we have to investigate the causes of this issue. The first cause could be that the sample weight used for the analysis was too high. So on the Duma software, you can check all the methods in analytics methods. Here you can find a library of all the methods that cover a wide range of samples and all different types of sample. And inside this library, you will find for each sample type, the recommended sample weight. Like only we recommend 200 milligrams of sample, and the maximum sample weight 300 milligrams. This in order to avoid this issue. Okay, the second cause could be that the purity of oxygen used for combustion is not as required, so not 5.0 purity degree. Again, you can check the purity as I showed you before in system analysis condition. Again, check if any leak is present inside the system. Another cause could be that the consumables are exhausted. So we suggest to check the status of the consumables before starting the analysis. You can check the status of the consumable on the Duma software. Okay, so in the service menu, under the voice maintenance, you can see the list of all the consumables of the NDA, their lifetime, and the runs since the last maintenance. Okay. Velp nitrogen analyzers works with Velp original consumables. The most important consumables that affect your results are the ash insert, that could be made of quartz, metallic, or ceramic. The combustion reactor that contains the Velp catalyst that helps the complete combustion of your sample, and the reduction reactor. The reduction reactor is filled with Velp V copper. The Velp V copper, when reduced, has this red color, and when it's exhausted, so oxidized, it turns from red to black. The last consumable is the water trap that is filled with that is a chemical trap filled with anhydrone. Okay, so in this case, when you find a tailing shape, the main cause of your asymmetric shape is that the reduction reactor is exhausted, because when exhausted, the copper cannot convert the nitrogen oxide into the elemental nitrogen. So the nitrogen oxide will arrive to the TCD together with the elemental nitrogen, giving this particular shape to the curve. Okay, here an overview of the Velp consumables. As I told you, the combustion reactor, the reduction reactor, and for the water separation, there is the water trap one. That it is a physical trap that there's no need to perform a maintenance for this kind of water trap, and the water trap 2, that is a chemical trap filled with anhydrone, and anhydrone, when exhausted, it has a compact aspect. So you can remove it and replace with fresh anhydrone. Okay, trouble number 4. In this case, the shape of the peak is okay, is correct, but you find a low precision of your results. How can you see the low precision? You can, thanks to the Dumasoft, calculate, as I told you, the relative standard deviation. So we have to focus on the relative standard deviation. That is calculated as standard deviation on average %. The official method says that for the Duma method, the RSD has to be lower than 2%. Okay, so what are the possible causes and the action to carry out to solve this issue? An important factor is the sample preparation. In fact, on the contrary of the Kildall method, the Duma method requires a small amount of samples. So the homogeneity of the sample is a very important factor to guarantee to use a representative aliquot. So in this case, for the sample preparation, if you are using a solid sample, you need to homogenize it with a serial, with a bench serial mill or a grinder, in order to have a sample with a particle size lower than 0.5 millimeters, as declared on the official methods. And if the particle size is lower, the better will be the results. Otherwise, if you are using a liquid sample, you just need to take the aliquot under stirring conditions. So you can put the sample in a beaker, and then mix it using a magnetic stirrer. Okay, the second cause could be that the method that you are using is not the most suitable to guarantee the complete combustion of the sample. So again, as I showed you before, in the analytics menu methods, you will find a list of all the methods developed internally that cover a wide range of samples. So you can choose one method from them. But if you don't find the correct method, you can develop a new one starting from 0. So how can you develop a new method? Here you can find a guideline for developing a new method. The 3 important parameters are the sample weight, the oxygen flow rate and the oxygen factor. The first, the sample weight, depends on the homogeneity of the sample. So if the sample is homogeneous, you can start from 50 milligrams of sample, perform 5 replicas, and see if the RSD is lower than 2%. Otherwise, if the sample is not homogeneous enough, we recommend to start from 150 or 200 milligrams. So again, perform 5 trials, and if the RSD is lower than 2%, the sample amount is okay. Otherwise, if the relative standard deviation is over the set value, increase the sample amount. When you increase the sample amount, check if the calibration curve that you are using is still suitable for that sample weight. Generally, the absolute nitrogen content of the sample should fall in the middle of the calibration curve. Again, think about that the higher is the sample amount that you are using, shorter will be the life of the consumables. The second parameter is the oxygen flow rate. The correct oxygen flow rate depends on the matrix of the sample. So if the sample is liquid, we suggest to select an oxygen flow rate of 300 milliliters per minute, like beer or milk. Or if the sample is solid, like pasta or flour, the correct oxygen flow rate is 400 milliliters per minute. The last parameter is the oxygen factor. The oxygen factor is very important because the Dumas doses the oxygen in a stoichiometric way. So once you compilate the database with the sample weight, thanks to the oxygen factor, the Dumas software converts the milligrams of sample into oxygen volume, so milliliters of oxygen. The correct oxygen factor depends on the matrix of the sample. So if the sample is liquid, the oxygen factor range starts from 0.5 to 1.0. Otherwise, if it is solid, starts from 1.0 to 2.0 milliliters on milligram. Okay, we recommend to start from the highest oxygen factor. So in case of liquid, 1.0, in case of solid, 2.0. And perform 5 trials. If the in this way, you guarantee the complete combustion of the sample. Once you find that the RSD is lower than 2%, you can start working to the optimization of this of the method in order to find a compromise between the complete combustion of the sample and the lifetime of the consumables, in particular the reduction reactor. So we suggest to starting from that oxygen factor value and reduce it step by step, and perform every time you reduce the oxygen factor, you perform 5 trials and check if the RSD is lower than 2%. If the RSD is lower than the set value, you can reduce again the oxygen factor until you set an oxygen factor that gives you a RSD that is over the set value. In this case, you make a step back and select the oxygen factor, the last oxygen factor that ensures you a complete combustion. Okay, even in this case, we suggest to check the status of the consumables and replace them with fresh ones if exhausted. To be sure that you use gloves when handle the tin foil in order to not contaminate it, and to perform a leak test. The last trouble is the low accuracy of the sample. In this case, the shape of the peak is correct. The RSD is good, but the results are far from the expected value. The accuracy issue is strictly correlated to the calibration curve, because as I told you, the calibration curve correlates the area of the peak to the milligrams of nitrogen. So if you are using the not correct calibration curve, the results will be far from the expected value. Okay, again, to create a calibration curve, we suggest to use standard sample, certified standard samples with a known nitrogen content. Internally, we use and we supply EDTA as a certified standard, and generally it contains 9.57% of nitrogen. Okay, on the DumaSoft you can create new standards and specify the nitrogen content and the nitrogen range. So before starting with the analysis, always check the calibration curve, performing a standard sample as an unknown sample. So in order to be sure that the sample nitrogen content falls inside the range specified on the certificate. Okay, again, you can check, you can see all the calibration curves on the DumaSoft. On the analytics menu, calibration. Here you can find all the calibration curves when created are saved inside this library. Inside this library, the user can check all the calibration curve and manage them. If you click on the desired calibration curve, you can see the details of the curve, so the calibration, so the sample weights and the R-squared value. In this case, the calibration curve is very good because the R-squared value is 0.9999, so it has 49 after the comma. Okay, to create a new calibration curve, you need to start with the calibration blank and then analyze at least 5 or 6 points of the certified standard. Generally, the calibration curve is made with sample weight intervals of 10 milligrams. As you can see here, we created a calibration curve starting from 10 milligrams up to 50 milligrams, and it covers a range of absolute milligrams of nitrogen from 0.957 to 4.785 milligrams of nitrogen. Okay, so generally we suggest to not create a too wide calibration curve, but to split it up into shorter calibration curves specific for the different samples. So the accuracy will be improved in this working in this way. Once you perform an analysis of an unknown sample and you find out that the calibration curve was not the correct one, there is the function recalculate. In this case, there's no need to perform the analysis of the sample again, but on the DumaSoft, you can select the line of your interest, in this case pasta, select with the left key, then the right key of the mouse. There is the function recalculate. Here you can recalculate your results, switching from the old calibration curve to the new one. In this case, you can see the nitrogen percentage old with the old curve and the new nitrogen percentage. Okay, so now the analytical troubleshooting is ended, and we spend a couple of words on the Velp Hermes. Velp Hermes is the in-cloud platform that allows the operator to be connected anytime, anywhere with the analytical with a elemental analyzers series. So you can do it from different devices like a personal computer, smartphone, or tablets. If you need further information, you can check our website that is updated periodically with new application notes, or you can contact us directly on the analytical department email that is analyticalsupport@velp.it. So now the presentation is ended, and I leave the word back to my colleague Paola. Thank you.
So thank you for your attention. Now we will have a very short verification test. I just tell you the rules about this short verification test. You have only 3 questions, and for each question you will have 4 different possible answers. You have to choose only one single answer regarding this question. You have 30 seconds to answer to each question. And I kindly ask you to write your answer in the chat, and then we will see together which will be the correct answer after each question. So let's start from the first one. So question number 1. If you obtain a high blend value when you are analyzing a tin foil, it means an empty tin foil. This means answer number A, tin foil is contaminated. Answer number B, not correct gaseous purity. Answer number C, the autosampler could be dirty. And answer number D, all the previous answers. I just give you 30 seconds to answer. Okay, it's a high blend value. It's a topic that is the first topic that my colleague Matteo has introduced you. So when you are analyzing a empty tin foil, you should not see a peak, but just a flat line. Okay, so now I guess that everybody has answered in the chat, so let's see which will be the answer. So the correct answer is the number D. So all the previous answers, because you can obtain high blend value when a tin foil is contaminated. As my colleague told you, you have to wear protective gloves in order not to contaminate the tin foil. You have to check the gaseous purity, because in the installation requirements it's written which will be the purity of the gases, both for the carriers and oxygen. And also the autosampler could be dirty. You can have a sample that is not fall down during the previous analysis. So it's important to check all these steps in order to obtain a flat line when you analyze a tin foil. So let's go to the question number 2. So if the results of my sample have high reproducibility, the relative standard deviation higher than 2%. This means A, not correct sample preparation and homogenization of the sample. B, autosampler is not working properly. C, we have a blockage in the system. D, all the previous answers. Also in this case, we analyzed this case before when we can face higher reproducibility of the results. Usually for the Dumas analysis, it is required to have results with relative standard deviation below of 2%. It is a requirement in the, written in the official methods. So it's very important to have these reproducibility data lower than 2%, and this is due, let's see together the answer, to the A. So if we don't prepare in a properly way the sample at the beginning, we can obtain a higher RSD. It means to have a correct sample preparation and homogenization. As Matteo told you, the particle size of samples for Dumas analysis, as required by the official method, should be less than 0.5 millimeters of particle size. So for solid samples, and for liquid samples, it's suggested to take them under steering in order to have a representative sample before the analysis. Let's see the question number 3. So if during the analysis of the sample I can't get the expected nitrogen value, this can be due to the autosampler or not correct calibration curve, to the water trap, or all the previous answer. So it's very important to obtain the expected nitrogen value when we analyze a sample. So as Matteo told you, we have to take care of different aspects. And one of these aspects is in these answers. I just leave you just a couple of seconds more to answer. So the correct answer, just a second. So the correct answer is B, not correct calibration curve. It's very important to create a calibration curve with the range in order that the expected value falls in the middle of the calibration curve. So thank you very much for your attention. As my colleague Matteo told you, you can write us to our email. It's an analyticalsupport@velp.it. So we can give you a support and to answer to all your analytical questions. Thank you very much and see you to the next training. Bye.